Okay. Let's take a look at some more of these equilibrium problems. So we kind of started on this on Friday. Can you guys hear me?
Yeah.
Cool. Thank you. Oh yeah, sideways screen. So we started this on Friday, and I chose sort of a shitty problem, just to be blunt, to start on, because you ended up with this like cube root in the denominator, which threw me, and then I did an approximation to solve it, which is fine, but not the lesson I wanted to get across. So I picked a much better problem for today, where the solution works out really cleanly. So with these problems in general, you end up in this situation at the end where you end up having to solve some sort of algebraic question or algebraic problem. And the difficulty of those vary. I mean, the most hardcore thing you'll typically see on an exam is something where you have to use a quadratic formula. But the goal is not really to get you to be able to solve quadratic equations or estimate cube roots. It's to be able to understand this underlying chemistry. So I chose one that's straightforward to solve, so we can kind of focus on the chemical part and the things that I think are confusing for students. Okay, so let's look at this one. So this reaction, so we looked at the Haber process. We don't actually require you to really learn any reactions in general chemistry, which is weird. So when I'm talking about these, I'm just talking about them just because it seems to make more sense to me to, I don't know, it's the actual chemistry component for the course. But yeah, last time we looked at the ammonia synthesis for the Haber process. This is how you make hydrofluoric acid. If you've watched like Breaking Bad, they dissolve a dead body in hydrofluoric acid. It's pretty nasty stuff. Yeah, it's something you got to be careful with if you work in a lab. It leaches the calcium out of bones. But this is the way you could make it. So you could take hydrogen gas and fluorine gas and put it into a flask and let it come to equilibrium, and you'll form some hydrofluoric. I guess you call it hydrogen fluoride gas at this point, but it would, once it touched you, it turned into an acid. Anyway, how do we solve this thing? So let's set some conditions up first. We'll say that K is equal to 1.15. Actually, I'm going to say times 10 to the second. We don't have to use scientific notation. So K for this reaction is right around 100. That's the equilibrium constant. And then we're just going to say that 3 moles of every component, so meaning every chemical in the equation up there, 3 moles are those are all added to a 1.5 liter flask. And those are allowed to come to equilibrium. So the kind of the broad way we look at these problems is we'll say, like, what are the concentrations at equilibrium? This is a standard equilibrium type question. So you're given some initial starting point here where you're saying, okay, I take 3 moles of each of these. So I've got a 1.5 liter flask. So let's say I got a round bottom flask. It's 1.5 liters. So we're working with a gas here. So let's say I put in H2, fluorine, and HF. And it's 3 moles of each of these. I don't know how to write that out, but let's just put it on the outside. So we've got 3 moles of each of these components in there. Okay. And then we're just letting it come to equilibrium. So we're letting the reaction go. And we're trying to figure out what these final concentrations are. That's the experiment we're running here. So it's hard. I think one of the things that makes most of the chemistry courses as an undergraduate hard are that you really have nothing to, everything is kind of abstract, right? Like you've never run a reaction, or if you have, it's been pretty limited. So sometimes it's helpful just to kind of write things out to make things feel a little abstract. All we're doing here is we're filling a flask with a bunch of chemicals at one concentration, letting the reaction go, and then saying, okay, what are the concentrations after the reaction finishes? That's what equilibrium problems are typically asking. And that's what we're doing here. Okay, so where to start with this? The first thing is probably just to calculate the general concentration. So there's a couple of ways you can do this. You can keep things in moles, or you can calculate concentration up front. It's probably more intuitive to calculate it up front. So what are our concentrations here? So we're working in gases. So with gases, you have the option of working in partial pressures or working in like molarity. Generally, I'd work in molarity. So there's 2 different equilibrium constants that you can use here. One is Kp, which is, we'll have a little, it'll usually be denoted with like a little subscript there. And the other is Kc, which usually is just written as K. So the one we're given here, this is Kc. It's a concentration one. And I would just let the equilibrium constant dictate whether I work in partial pressures or whether I work in moles per liter. So if it's Kc, work in moles per liter. If it's Kp, work in partial pressures. And I just generally let whatever the constant is dictate my units. All right, so we come down here and we convert everything over to the appropriate concentration. So my concentration of H2 is going to be equal to 3 moles. And 1.5 liter. So this is 2 molar. And then for fluorine gas, it's going to be equal to the same thing because we're starting out with the same amount of everything. And the stoichiometry is the same for those. Well, stoichiometry doesn't play a role just yet. Yeah, they're just all equal to the same concentration. So I have 3 moles of each one of these, and they're all divided by 1/2 liter. And so I'm 2 molar in everything at the beginning. So those are my starting concentrations. Okay, so here's what kind of happens with these problems. I think the rice tables are really handy as far as like bookkeeping methods, but they give this impression, I think, a lot of times to students that, and I certainly was guilty of this as an undergraduate, but it gives this impression that like you can work out the problem by just kind of like following a recipe of writing out the rice table and just kind of pushing through all the numbers and getting a solution and not really understand what's going on chemically. And maybe if you're like hyper rigorous about how you treat the problems, you can develop sort of an algorithm for solving them that way. But it usually doesn't work super well. It's better if you can actually develop a little bit of a chemical intuition, which is hard. But I'm going to try and help guide you through that on this problem. So before we just start to brute force this thing with a rice table, let's try and consider like what the hell's going on here, so we can kind of have some like general idea of what's going to happen with the chemical reaction before we actually start solving it. So that we know when we kind of get to the end that we have some sort of checkpoint to make sure that we don't just have a number. Because I feel like a lot of times what happens at the end of these problems is like people will solve them, they'll get a number, and they'll just be like, all right, what do I do with this? What does this mean? And we don't want to think that way if we can avoid it. Okay, so let's start by writing out an expression for Q. So K is the equilibrium condition. Q, we can take at any point. I'm going to put a little zero on here. Let's put zeros on all of these, actually. So these are the initial concentrations. So like 0 meaning like T equals 0 at the beginning of the reaction. So Q here is going to be equal to HF squared. So the initial concentration of HF squared over the initial concentration of H2 over also the initial concentration of fluorine gas. And so that's my expression for Q. And so I'm getting these numbers. I'm pulling the values for one. I'm pulling the expression itself from this chemical equation. So remember that Q or K, whatever, the mass expression, the zero, the little knot on there is just like a way to differentiate that these are like the initial concentrations. You could use I if that's clearer for you. But usually we use a little knot to mean initial concentration. Yeah, so we're looking at, when we're writing the mass action expression, it's always just going to be the concentration of the product, and then we're going to put it to the power of whatever its coefficient is. So this is sometimes confusing for students because, you know, like, why do we square that? How do you know when to square? How do you know when to use the coefficients? You know, like, I don't know. It just depends on kind of how you were taught in your last class, whether it was in high school or at UT. But that square, you can just accept that as being like a fundamental, like, it's just like a fundamental piece of the expression. So people went out and studied what equilibrium constants look like, and we just know that the mass action expression always goes to whatever the coefficient is of the concentration. So for HF, we know just from studying it that it's going to go as the square because it has a 2 out front. And this one has a 1, and this one has a 1. So like this is just like, we kind of like, if you think about in physics, you know, you've got things like force equals mass times acceleration. Why is it work out that way? I don't know. Like, that's just the way the universe is designed. So this is just like a thing that falls out of like the fundamental physics of reality. There's nothing to change about that. There's no algebra to worry about. That's what these mass action expressions are. They're just physical laws that we've discovered. That's going to be different than when we look at the algebra later. But yeah, so what does Q end up equaling here? So we've got 2 squared divided by 2 times 2. So Q equals 1. Oh yeah, I turned the gain down a little bit just because it was looking really red. I can turn it back up. Yeah, so Q ends up equaling 1 there. And I've chosen these numbers carefully so that, good. I've chosen these numbers carefully so that it equals 1. What does that mean, though? What does it mean for Q to equal 1? So Q is different from K. This is at equilibrium. This is not at equilibrium. So what are the possible values for Q? Yeah, what are the units for K? I'll come back to that in a second. What are the possible values for Q? The possible values for Q are pretty much anything other than K. So greater than 115 or less than 115. You can have any value for Q, but K can only be 115, at least at whatever pressure and temperature we're at. Yeah, what are the units on K here? So the units on K they vary depending on whatever chemical reaction you're looking at. And for this one, it ends up just working out to being dimensionless. The units sometimes are like really weird. They'll be like mole liters squared and stuff like that. It's not the worst thing to just think of K should really be dimensionless. And that gets into this thing of activity coefficient or activity coefficients, which we're not super worried about. The important thing about K, more so than the units, not that the units are necessarily bad to carry over or worry about, but the important thing about K to remember is that it's constant. It's a constraint that doesn't change. The units aren't super helpful. In the same way, I guess I'm saying that in the same, like, like when you think about velocity or something, it's important to know that the units are like meters per second. When you think about the equilibrium constant, the units don't really actually help you that much in terms of kind of thinking about things. But okay, all right, I'm gonna try this poll thing. So I'll ask, one of the problems I have with the Zoom thing is it's hard for me to ask questions and then know when everybody's done because usually in class I can like see people when they start to get restless and pull out their cell phones and chat. And here I just, I don't really get a good feel for that. So let me try this thing. So I launched the poll. I haven't done this before, so probably my monitor will explode or something. But the question is, I have Q equal to 1. What does K end up equaling? Or not, what does K end up equaling? God damn. Which way does the reaction shift? Okay, so if you put towards products, that is the correct answer. Any of the other answers towards reactants or won't move are incorrect. You're not getting graded on this. This is just for me to understand how much I have to work at this. How do we know which direction it's going to go in based on what the values are? One way to know is just to memorize that for Q less than K, it's going to shift to the products. That pretty much tells you everything you need to know, because if you know that, if that's true, then Q greater than K means it must shift to the reactants. And then you just have to know that Q equal K means it doesn't move at all. But so Q less than K, it shifts the products. But you can get this information just by looking at the math of this thing. If Q is equal to HF, the initial concentration, and that's equal to 1, and K and that's equal to 115, all you have to do, which you want to think about here, is I've got this expression where I have some stuff in the numerator and the products in the numerator and the reactants in the denominator. Which of these numbers needs to get larger in order to have this expression for Q end up equaling K? So when Q is less than K, let me say it a different way. When Q is less than K, so it's equal to 1, I need this number, or I know that this number needs to get larger. And it's going to get larger by changing the concentrations of these chemicals that are in the flask. So these things are all going to start changing, and they're going to change in such a way that this drifts towards 115. So these numbers are all going to change, and we need this number to become 115. How can that happen? So one way is to make the denominator, so the concentrations of hydrogen gas and fluorine, smaller. And the other way is to make the numerator larger. So the concentrations of the product's larger. So the product concentration, if you want to just think about it simply, the product concentration must go up in order to make this bigger, to make this equal to 115. So we know that HF is going to increase, and we know that things are going to shift to the products. So I would sit with that if that doesn't make sense and be able to do that kind of analysis. There's a relationship there as well, that as reactants, as you form more products, that consumes reactants. It sounds, when I say it, it sounds like almost obvious, but it's kind of hard to tie all these things together, which is that it's just saying that like the HF gas that I form in this reaction has to come from somewhere. And it comes from consuming H2 and F2. So as this goes up, these concentrations must go down. It's all the same stuff that you understand from reactions that just go to completion. Just now we have this extra element of calculation we have to do in there. Okay, but this is useful information. So now we know that at equilibrium, the expectation is HF will increase and H2 and F2 will decrease. So this is trying to build in some thinking around these problems that we're solving, right? This is kind of an important thing in order to solve these, especially as we get into the acid-base chapter. There's a lot of stuff to kind of connect and think about. So just kind of plugging into Rice tables, it's probably not going to serve you super well, unfortunately. So try to understand stuff at this a little bit deeper of a level on the chemistry scale. So if this isn't making sense, hang out afterwards in office hours and ask more questions. Ask questions on Piazza. If it was real life, if we could actually meet in real life, we'd have some sort of study hall or something. Okay, so that's sort of a qualitative overview of what's going on there. We're going to expect these changes to happen, but how exactly is it going to happen? That's when we have to start worrying about some math. So let's take a look at our equation again. Let's forget about the equilibrium for a second and just look at it going in the forward direction. So under normal circumstances, if I have 1 mole of hydrogen gas, and let's say I react that completely, so this is like, these limiting reagent problems we'd look at, how many moles of hydrogen fluoride gas do I expect to form? So if the reaction goes to completion, and I completely react 1 mole of H2 gas, how much HF gas forms? Not an equilibrium problem? Yeah, 2. Getting some answers of 2. So this is an important thing. So again, it's easy to forget this stuff, so I'm certainly not shaming anybody for this, unless you're a professional chemist, in which case you should probably know how to do that, but I don't think that's anybody in here except for me. But yeah, it's really, really important that you remember this stuff from General Chemistry 1. So again, if this isn't making sense to you, hang out in my office hours or go and talk to our TA, Ryan, during his office hours and get a handle on this. It's like a fundamental thing in order to be able to build on. Yeah, so we'll form two. If I have 2 moles of hydrogen gas, let's say I change it slightly, and I react that completely, how many moles of HF will I form? 4. So there's this relationship between these. This is where these algebraic expressions come from. One way to say it is that for every, or so the between what these numbers out front of this are, it tells you the ratio that these things react and form in. We know that if 1 mole of H2 forms, 2 moles of HF form. If 2 moles of H2 reacts, 4 moles of HF forms. If 4 moles of H2 reacts, 8 moles of HF forms. So even if I don't know anything about a reaction, like let's say I just have this general formula up here, what it allows me to do, it allows me to calculate how much HF I would form from H2 if I reacted it completely. It tells me the exact ratio that these things react in. So for traditional things where things are going to completion, this was fine and we could use this to solve things. Now we have to do a little bit more fancy work, but it's essentially the same problem. So this is not necessary to like kind of solve the problem. It's more for how to think about where these variables come from. So if I have X moles of H2 gas, like let's say I react X completely, how much HF do I form? Transfer function. That sounds like some chemical engineering stuff. I don't know because I've never taken transfer. I hear it's kind of a painful class to take. Unless it's a name for something that I know and I don't realize I know it. Oh no, it's talking about a Laplace transfer in my Google search. Yeah, I have no idea how that's related to the transfer function. Good question. Yeah, HF here is just equal to 2x. That's where these numbers are coming from. That's why I know that, that's why I can write out, that's where the 2 comes from, I guess I should say. Sometimes people get confused. They'll look at this number, you know, these subscripts on here. They also get confused about like, you know, like maybe I should square this because it's squared somewhere else. Like that's all we're doing here is we're saying that if this is X, this is 2X. And that's just another way of saying that like when this is 1, this ends up being 2. When this is 2, this ends up being 4. It's just an algebraic way of stating that thing that's kind of a little bit intuitive. And then we know that fluorine will just be equal to X because for every 1 hydrogen I have, I end up having to react 1 fluorine. And we could use something besides just 1x, right? If we wanted to make it more painful, we could use 0.2 for this and call this 0.4. It doesn't really matter. As long as that ratio is correct, we'll end up getting the correct answer in the end. So since we don't know, since the reaction's not going to completion, yeah, it's just with the coefficients. So if you're just trying to like, yeah, it's just with the coefficients. So you find, my recommendation for setting the variables is find at least one of these things that has a 1 in front. That's the easiest thing to do. And you set that equal to X. And then you just take everything else and multiply it. Like this one becomes 1x, this becomes 2x. That keeps things simple. So since we don't know what the concentration changes are exactly, and we have this coefficient or this equilibrium problem we're trying to solve, having these expressed as variables is actually really useful. And that's when the Rice table kind of comes in. So I guess what I'm trying to get you is to just try not to let your brain completely shut down when you write the Rice table out. There's stuff that's happening there that's important, that's related to the chemistry. So we have our reaction. Our initial concentrations are what we calculated already. Those are all 2 molar. The change is what we've looked at here with these variables. So I'm just saying that I don't know exactly how much it's going to change, but I know that for every amount X that I lose in terms of hydrogen gas, I'm going to gain 2X of HF. And for every X amount of hydrogen gas that I react or lose, however you want to think about it, I'm going to need X amount of fluorine gas. What happens? Yeah, it's a good question, Udita. So Udita's question is, what if H2 is increased by 2 moles and F2 is increased by 3 moles? Uh, I think another way of saying that is like, what happens the ratio? That's initial, I. If you go back up to the top, the initial concentrations are what that is. So we start out with 3 moles in a 1.5 liter flask, so it's 2 molar, yeah. But yeah, so Udita's question is like, what happens if I change something about the concentration? So I have 2 moles of H2 and I have 3 moles of F2, let's say initially, instead of when I'm starting out the problem, instead of just having everything 2 to 2 to 2. Doesn't matter. This here, the initial, could be anything. This algebraic expression here holds no matter what the initial and final concentrations are. That derives directly from the chemical equation up here and is independent of the starting reactions. Yeah, it's unrelated to this number in the sense that, like, yeah, it's just unrelated to that number. These are just ratios of how the things come together. I guess another way to look at it, if you want to relate it, if you want to think about it in terms of something macroscopic, like if you think about a cookie recipe, right? If your recipe calls for, like if I have a recipe that calls for 1 cup of brown sugar and 1 cup of white sugar, and I want to double that recipe, what am I going to use? I'm going to use 2 cups of brown sugar and 2 cups of white sugar. If I want to triple it, I'm going to use 3 cups of brown sugar and 3 cups of white sugar. The ratio between these then would be, I could call that X, and this would be X. So if X equals 1, then this also equals 1. If X equals 2, then this also equals 2. That ratio holds. If I go in my pantry and I have, you know, a giant, like, let's say like 25 kilograms or something of white sugar and a truckload of brown sugar, or I just have 10 cups of each, it doesn't affect this ratio at all. Right? The recipe is not affected by how much I have. The recipe is sort of its own independent thing. How much I have might dictate ultimately how much I can make, but the recipe itself is independent of how much stuff I have there. So just like when you are doing, just like when you're doing a recipe in the kitchen, it doesn't matter how much stuff you're starting with, as far as what the ratios of things are that you add. Okay. So be careful with that stuff. I know from like working with students, like one-on-one, that this stuff can get pretty messy. Since we know that the reaction is proceeding towards the products, it makes sense to keep the sign on X consistent with that. So we know, so one of the things of knowing that Q is less than K and that the reaction is going to move to the products is it allows me to say that, well, like, I know I'm going to be losing some amount of H2 and I know I'm going to be losing some amount of F2 and I'm going to be gaining some amount of HF. It'll still work out. If you get the signs mixed up, it'll just be more confusing. Okay, so what does this mean? This tells me that at equilibrium, these are my concentrations, which is ultimately what the problem is asking me for. So I know that at equilibrium, it's going to be 2 molar minus whatever the amount is of H2 that reacts. For fluorine, it's going to be the same thing. It's going to be 2 molar minus some amount X, and that any of that that I lose is going to be picked up as HF over here. So that's going to be 2, which is what I started with, plus 2 times x. Yeah, 2x, I just gapped. All right, so now I want to make sure, now is when I actually solve the problem. And I just plug in these values. Let's start out writing it. So I write out my mass action expression. And now I just want to plug in these values. So remember that Q we calculated using the initial concentrations. And we came out with 1. Now it's like, this is like, I'm not going to put the F on there, but this is like the final concentration. So after this has come to equilibrium, what are my final concentrations? And so I plug in these algebraic expressions I've made, which is to say that I have, at equilibrium, I know I have 2 plus 2x over 2 minus x times 2 minus x. And I know that the equilibrium condition is that this has to equal 115. So I don't know, so whatever the power of the equilibrium constant is, that it allows you to calculate what these concentrations are, even though the reaction doesn't go to completion. And so I can solve this.
Square.
Thank you. So this one's set up to be super easy to solve. I just take the square root of both sides. And then eventually, just standard algebra at that point. We solve for x and we get x equal to 1.53 molar. So usually I think when I'm hanging out with students and we're kind of working through this, we'll get to this point. You know, this part, this makes your brain shut down and go into how do I solve algebra stuff. And then I get x and it's like, all right, I solved x. But the original question is not what is x, right? It's what are the equilibrium concentrations? And so I've defined my equilibrium concentrations here. I said HF is equal to 2 plus 2x. This is another place where people get confused with the square. Like, what about the square? Do I have to worry about the square? The square is not matter here because I've defined the concentration of HF as 2 plus 2x. If you're confused on that, don't feel bad. That's a common point of confusion. Hang out for office hours and we can clear that up. But so I have all these definitions. This is how I defined all of these. I said that I know for HF, I start out with 2, and then I gain 2x. For H2, I start out with 2, and I lose x. F2, I lose x. And then so I just go in and plug these values in. So at this point, we're done with the problem for the most part. But we still have to, if you want to have some instinct of checking if this is correct, we can check first to see, remember that we knew that Q is equal to 1 and K was equal to 115. So we're expecting to form products. That was the first thing we looked at. And so is that true? If our initial concentrations of everything, so HF, so HF was equal to H2 these were all equal to 2 molar. Did I form products? So HF was initially equal to 2 molar. Now it's equal to 5.1 molar. So yeah, I did form products. I also lost reactants, which is what you expect. You shouldn't be able to form products without losing reactants. Oh yeah, thank you. Yeah, so I picked up product. So I went up in terms of product concentration, which is what I expect. And I lost reactant, which is what I expect as well. And it makes sense on some intuitive level. It's hard to keep everything together, but it makes sense that, you know, you can't gain products without losing reactants. There's this, you know, conservation of mass. It's a basic physical law. Yeah, I just wrote them in the wrong order. Sorry about that. Let's see. The only other thing that I would say that you can do to check to make sure you're right is to go ahead and plug these things back in for K. So if K should equal 115, I should be able to plug these values back into my K expression. And I should come out with approximately 115. So in the last, last class period when we solved that problem, that would be a good way to check your, let's see. No, never mind, I take that back, because you'll end up getting the correct answer no matter what. This is, sorry, I'm in my own head on that. This is a solid way to check this though. If this isn't true, then you've screwed up somewhere along the way in your algebra. So it's a good way to go and check and just make sure that the world makes sense. These two things combined are good ways to check at the end of the problem. So when you get to this number, remember that you're not done with the problem, even though it feels like you've been working on it for a long time. You still have to go in and relate it back to the concentrations. And once you go ahead and get the concentrations, we can do some reality checks on that by thinking about what Q is equal to, and also just checking to make sure that, you know, this thing does in fact satisfy the equation that we constrained it with. And this is generally how you solve these equilibrium problems. So this one works out really nicely here. Somebody have a question?
Yes, sir. The number was 1. So it wasn't 115. Is that a problem, or
So
maybe I
Q
messed
was
up?
equal to 1.
Yeah, Q. I mean,
Q is equal to 1. K, though, is equal to 115.
yeah.
Yeah, so Q, so this is I know it's confusing. So Q is, I'm not at equilibrium. I'm not at equilibrium, so I just plug in my initial concentrations. That's just what I started with, and that equals 1. That's a snapshot of the reaction, and it tells me how far away I am from K.
Okay.
This is after I let the reaction run and it comes to equilibrium. So Q is a non-equilibrium situation, and this is the equilibrium situation. One way to look at the equilibrium constant, the 115, is it tells you, like if you think about a reaction running completion, what you're really saying is the reaction runs to 100%. The equilibrium constant sort of tells you how far along it really goes. You know, so like an equilibrium constant of 1, well, 1 is a bad example because we're using that right now. Let's say an equilibrium constant of like 1 million tells you that the reaction does go close to 100%. An equilibrium constant of exactly 1 would mean that the reaction goes 50%. An equilibrium of like 10 or something, I should be able to do this. Well, I guess it depends on the reaction, but it might mean like 60 or 70%. Those values tell you how far along to the right it goes. When you're less than 1, it's less than 50% products forms. When you're above 1, it's more than 50% products forms. Q doesn't tell us anything about how far the reaction goes. It just tells us where we're at. Okay, so it's like if you're trying to go from, like, let's say you're going, I don't want to get too like out there with analogies, but like if you're traveling like a distance, if ultimately all of us, let's say we're actually going into UT today, the equilibrium condition would just be that everybody ends up at UT. Q is kind of like where you start at. You start at your house. How far away is your house? It's like it just tells you how far away you are from equilibrium. So here Q is equal to 1. If somebody was living even farther away from school, Q would equal to maybe 0.0001 or something, right? So the farther Q is from K, the more you're going to have to travel to get to the equilibrium condition. K is just where we finally end up. Q is where we're starting at. Q is not constant at all. Sorry, I know it's hard to think about this stuff just because it's, again, there's no experience with putting gases into a flask. Like, at least in physics, you've thrown a ball before or something, right? With chemistry, it's like, well, these are pretty foreign experiences. All I was saying, right, was that I've set this problem up to where this is easy to solve, where I end up with some square roots here, this is a really nice thing because now I can take the square root of both sides and easily solve for x. Typically, or more often, you end up with a square in there and you have to do a quadratic formula. I think we have some practice in there where you get to use the quadratic. You guys have access to your computers. You can just have a quadratic solver up on your computer if it comes to that. I wouldn't give you a cube even with a computer. I don't know how to solve those. The formula for it is ridiculous. You probably have to use some approximation method or something. But this problem provides a really nice general overview of the parts of the problem that you want to be able to understand. So if you're just going in and you're plugging in numbers and you can kind of halfway get there with a Rice table, if it even serves you well in this exam, which you might be okay, it's definitely not going to serve you well in the next exam and the exam after that. So make sure that you spend some time on this and try and get some of these ideas down, like why is x equal to this? Why do I not have to worry about putting the square here and that kind of stuff, and make sure you really understand that on some fundamental level. Yeah, that's my advice. And obviously you got to do what you got to do to try and just get through the goddamn test. I understand that you guys are doing a lot of stuff and we're in the middle of a pandemic, but if there's one thing that you spend a lot of time on to learn, it should be this. I don't know, we haven't made the exam yet, so I don't know exactly what the percentages are, but this stuff is so important. This stuff is so important for the rest of the course this semester. So Rice table, why does H2 and F2 have to be negative? So it doesn't, so the question here is why is this negative and why is this positive? It doesn't matter as long as you're consistent. So x could be positive for both of these, and you could put negative 2x here. That relationship has to hold. Like, these signs have to be opposite as you cross over the reaction arrows. But it makes sense to my human brain, at least, to use minus x because I know that q is less than k. So I know I'm going to be forming products, which means that if I'm forming products, I'm going to be gaining over here. That's why it's plus 2x. And I'm going to be losing over here. So that's why I'm minus x, right? Algebra will work out regardless if I make that plus x on the left-hand side. It just doesn't make sense to me intuitively. Yeah.
So it's forming products because the coefficient of HF is 2 and the coefficients of the reactants are both 1.
No, the real reason.
Without solving for Q,
So without solving for Q, unless you have no products that you're starting with, without solving for Q, you have no idea which direction it's going to go in. The Q tells you where you are. It's kind of like to go back to the analogy of everybody kind of driving in a UT. If you're trying to figure out, it's like the analogies don't hold exactly because it's chemistry and it's weird, but it just tells you, it tells you where you're at. So like if you get lost, Q would tell you, did I go past the university? Like, do I have to go backwards, or am I still going towards the university? it tells you which direction you need to go in to get to the university. That's what Q tells you, but it's very dependent on the starting conditions that you're given. Like you need to have coordinates for where you're at in order to understand where you're going, if that makes any sense. Like K is just where you're going. The ratio of the problem is just like a recipe for the reaction. But Q is actually like, okay, we're in a real life experience. We're having a real life experience with this. Where am I at relative to these kind of standardized things, K and the ratios?
So best practice is to solve for Q, then solve for K.
Yeah, it's good practice to do that, I think. Solve for Q, understand where you are relative to K, so you have some idea of what you're doing as you move forward with the problem. And it gives you a really good idea, I think, of what the hell K and Q are. So after you solve 10 of those problems, hopefully it starts to click a little bit. So I guess what I would say is you don't absolutely have to solve for Q in order to solve for the final concentrations, but it is a useful thing to do because it keeps your algebra signs like consistent in a nice way and gives you some idea of whether or not your answer is correct. And it builds your chemical in terms of practice, it builds your chemical intuition for working problems. But yeah, it's confusing as hell. I understand that. Like, what is the relationship between like these numbers that are just coefficients to Q and K, and also to all these algebraic expressions tends to take a little while to kind of click for everybody. So don't be disappointed if you're struggling with that. All right, let me go get some water, and then I'll be right back, and we will do we'll do some office hours.
Thank you, sir.
Yeah, thank you guys. Okay. Let me get the chat window open here. Well, you guys are obviously welcome to unmute and ask questions at will. All right. Yeah, so that's equilibrium in a nutshell. At least the I don't know, I think the more difficult, or some of the more difficult problem solving aspects of it. We'll also go through, I guess, some other equations that relate K, which is really what you're doing, back to free energy through things like this equation. That's also pretty important. But that stuff's not that bad compared to the Rice tables. Can you explain number 20 on homework number 2? Maybe. Let me pull it up. Oh, it's colligative property stuff. All right, so the question is, damn, we had 20 questions on this somewhere. Catalase. Oh, yeah. Yeah, I can explain this one. I didn't do a great job of preparing you guys for this exact homework question, but this is a reasonably standard, like, colligative property question. It's just one extra step. So okay, so number 14 in homework 2. Yeah, I can come back to that. Yeah, so the question is, we've got some enzyme, catalase, and it's in water. And we know that 14 milliliters of it containing a certain amount of that enzyme exhibits a certain amount of osmotic pressure. And it's asking what the molar mass is. So the experimental setup for this is, or one way to do it, you put pure water over here, and then on this side, you put your catalase with the same volume of water. Oh, nothing is coming. Oh, for some reason it paused it. There we go. Yeah, so you set up one of these like tubes. Here you have a barrier that's semi-permeable. So water can pass through it, but your enzyme cannot. Over here you have your catalase solution. And you've set it up to where these are the same volumes here. Let's see, so we've got 0.166 grams of catalase. Yeah, and so this is 14 milliliters. This will also be 14 milliliters on that side. And so you let the thing come to equilibrium. So you let it settle for a while. And water will start to flow from the pure solvent side to the solution side. So you're going to expect the volume to decrease over here and to increase over here. Osmotic pressure. It's telling you the osmotic pressure. Yeah, so I'm trying to think exactly how this is expressed. I guess the distance between here and here is the osmotic pressure, essentially. And so we can use this to kind of back calculate what the molecular mass is. So the osmotic pressure equation is this. For some reason, they use pi for this, and it's related to the molarity times the ideal gas constant times the temperature. So they're being a pain in the ass here, and they're giving us our osmotic pressure in torr. So let's see. So R here is going to be equal to 0.82 liter atmosphere per mole Kelvin. So like I generally say, I let whatever the constant that I'm using is, like whatever physical constant that I'm using, dictate all of the different units. And so since we're given the osmotic pressure, which is pi, in torr, we have to do this straightforward conversion. So we come up with 1.473 atmospheres. Okay, so now let's see. Yeah, so now we know pi. So yeah, we can take back. So now we just look at our equation. So we know pi. We have a value for that. We know R and we know T. This is just the constant. And then T, I'm hoping they give us to us. Yeah, they give it to us. And the problem is 20 degrees Celsius. And so we know molarity it's going to be equal to moles per liter. Yeah. I mean, yeah, I mean, on the online test, you just type into Google how many torr atmosphere or whatever. That's what I do in general. And but yeah, so then we can take this. So basically what this equation allows us to do, though, well, the way this works is we know how much catalase we dissolved into the 14 milliliters. And since we know the osmotic pressure, which we've measured, we have this relationship that allows us to take the osmotic pressure and relate it to the number of moles of solute that we have there. So because colligative properties are independent of mass and all that kind of stuff, it's only dependent on the total number of moles in solution. That's what allows us to have this relationship where you can derive the molecular mass. So we can solve this equation for molarity.
Do we have to convert the temperature?
So again, because it's in Kelvin. Yeah, thank you. I was about to say again because of the ideal gas constant, but yeah, you're right. So yeah, so T is equal to 20 degrees Celsius, which is 298 Kelvin.
Don't you also have to multiply the equation by the Van Hoff factor?
So yeah, I guess that's something that wouldn't be clear to you for, so we can put the I out front. I guess that's something that wouldn't be clear to you just if you don't know anything about enzymes. Enzymes are not, the Van Hoff factor is always, well, yeah, the Van Hoff factor is always 1 for an enzyme, certainly in our class. So so you have to include it, but it's going to be 1. So it doesn't actually end up mattering.
So if they don't give you like a reaction or like something, we would know how to calculate the Van Hoff factor if we just assume it's 1.
Yeah, the only time that I'll say that I'll state what you said a little bit different, which is the only time you have to worry about the Van Hoff factor is if you have something that's ionic. And the only things that are ionic, you guys kind of know the universe of ionic stuff, like it's sulfates and chlorides and those types of things that we know how to name. So if you have to get the Van Hoff factor involved, it's typically going to be with something that you at least are familiar with, like you would know how to write out. Everything else in the universe, more or less, has a Van Hoff factor of 1. 293, did I mess that up? Oh yeah, I'm sorry. I'm used to 25 degrees Celsius from the being room temperature. Yeah, 273. Okay, so yeah, so fine. But once we get all of our conversions down, now we can go ahead and plug in. Let's see. So we put in 1.47 times 10 to the minus 3 atmospheres divided by 0.0821 liter atmosphere per mole Kelvin times our temperature, which we converted. That cancels out. That cancels out. And then moles is on the bottom, so it'll end up on the top. So yeah, you come out with a really small number. So you're close to being done with this problem at this point, but remember it asks for the molecular mass. So we know, so this is the molarity of the solution. So let me rewrite this. Let me write it down here. Let's see, so this is the molarity of the solution that contains 0.166 grams of catalase per 14 milliliters. So using those two things, now we can figure out what the number of grams per mole is. So if we know that there are 6.1 times 10 to the minus 5 moles in 1 liter, you can say, well, I know that there's going to be some number of moles in 14 milliliters. And I can solve for n. It's hard, like, I look at these numbers and I'm like, I don't have a good feel a lot of times for what they should be, but It makes sense at least that there's less moles in 14 milliliters than there are in a liter. So this, you expect this number to be smaller than this. That's about the best I can say in terms of checking your work as you go here. Okay, but that tells me the number of moles. And then by definition, molecular mass is in grams per mole. And so we know that there are 8.5 times 10 to the minus 7th. Oops, sorry. We know that there are 0.166 grams per 8.5 times 10 to the minus 7 moles. So I come up with this kind of large number, 1.94 times 10 to the 5th, assuming I did my math right, grams per mole for catalase. But the key thing here is, so is this reasonable? Yeah, enzymes are usually really big, so they generally have pretty high molecular masses. I don't know exactly what they are, but it seems reasonable to me. But the key thing here is that you can tie in the number of, we can use this equation. If we know the osmotic pressure, then we know the molarity. And if we know the molarity, then we know the number of moles in the original solution. So osmotic pressure allows us to calculate the molarity of the original solution. And if we know the mass, in the original solution, so that's given in the problem. Maybe we can put in another step. We can use that to get the moles of the original solution. Moles. And those two things we can combine to get the molecular mass. But ultimately, to determine the molecular mass ever for anything, you have to figure out, you have to know the number of grams of stuff that you have, and you have to have some way of figuring out the number of moles that you started with. So if I know the original number of grams was a 0.166, and I can calculate the original number of moles, all I have to do is divide those two numbers, and now I have the molecular mass. So that's pretty, it's just like, I don't know, when you do chemistry for a while, that makes sense. When you don't, I think it's less clear. So this is a workflow for how to do that. Yeah, I just uploaded the problem session for last week, at least for Friday. I thought I had uploaded the other ones before, but I uploaded them this morning at like 6 or 7.
The answer for number 20 on Canvas is just like a tiny bit off. Like it's like 1.8 something.
Oh yeah, I might have made an error somewhere, or the Canvas problem is off. I'm not sure.
Okay, so the process is the same, I guess.
The process is correct. Yeah, that I'm 100% confident in. Oh, they have the answer. I can look at the editable version. Let me see. Yeah, they came up with 1.8 times 10 to the 5th. I came out with 1.9. Yeah, I don't know. It's off by like a tenth of like a tenth, so it's probably fine. But yeah, I might have accidentally kept a 1 or something, or dropped a 0 somewhere.
Because you used 8.2 for the real constant instead of 8.206. If you use that, you would.
Oh, okay. As opposed to 8.21.
And they have a tiny explanation when you submit it, and it said 0.00158 ATM instead of 1.47. So I guess
Oh, is that what the problem was?
like the when you converted the.
Oh,
I found
this,
that,
my conversion's off. What
I
did we
don't
start
know,
out
like
with
when
in
you
terms of? Oh, yeah. I see what the problem is. I converted 1.12 Tor, and I should have used, for some reason, I like mental error to converted 1.12. Hold on. Let me see. Yeah, I think I punched into my calculator wrong. Yeah, that's the problem. This number here is off. This should be 1.5 times 10 to the minus 3 atmosphere. So yeah, that's off by 0.1, which is why the final answer is off by, I guess, 0.1 in this case.
For
So
these,
yeah, all these numbers are fudged a little bit, but the fundamental idea stays the same. What was the question?
For the Tor conversions, you said for like an online test where you just Google like Tor to atmospheres, or?
That's what I would do, yeah.
Okay.
I don't know. I mean, you can do them by hand if you're more comfortable with that, but Google, like the search bar in Google will do conversions pretty rapidly.
Or Google like ideal gas constant on Wikipedia, or?
Yeah, just pull it up. I mean, you might want to put together a crib sheet or something because it might be faster. It just depends on how fast you are at kind of moving around online. I guess my main point is just that there's no reason to where you don't have to, the test is not designed such that you have to memorize all of these things. So, you use the resources that you use, the fact that it's open book to your advantage, however you want to do that, whether you use Google or whether you use a book or something.
Okay.
But yeah, so that's how you work those problems. So, this is not a completely insane experiment to do. If you're isolating a protein, let's say, and you don't know anything about it, this would be a way to calculate the molecular mass of it. Because it's a way to know exactly how much it weighs per mole, which is, I guess, difficult to do in some other ways. So this is like a cheap way to figure out the molecular mass of a protein. So if you're working in like a unknown protein, for example, this may be, I don't know, I've never worked in that field, but this might actually be just the starting point for figuring out the molecular mass of it. Let's see, assuming that it's pure. Yeah, semi-permeable membranes are kind of weird, but this is essentially like how, like when people go on kidney dialysis and stuff, this is essentially how that works. Like an artificial kidney or something has a semi-permeable membrane that can be used to kind of filter out salts and things of that nature. All right, let's see. The other problem was, I might have uploaded them and not made them public. I'll go and check that after this. For the lectures from problem sessions from last week. Graph on number 14. Oh God, yeah. Substances A and B are mildly volatile solvents. Use the diagram below. Determine the mole fraction of B when the vapor pressure of the mixture is 80 torr. Got this graph. It looks like this graph is scaled, like they give you little increments on there so you can kind of figure out what's going on. I don't think I'll be able to accurately reproduce those, but yeah, all right. So what the hell's going on in here? So it says substances A and B are mildly volatile solvents. Using the diagram below, determine the mole fraction of B when the vapor pressure of the mixture is 80 torr. 80 torr. So 80 torr is going to be right here in terms of pressure. So I think this is just testing your ability to read graphs. Although this is a kind of a weird ass graph. So substances A and B are mildly volatile. Using the diagram below, determine the mole fraction of B when the vapor pressure of the mixture is 80 torr. X of A. There's 3 lines on there. Let's see. So I think yeah, so I think the way these graphs look, this is a weird, it's weird because they haven't labeled this very well. So X of A is increasing in this direction. So this is the partial pressure of A here along this line, and then the partial pressure of B is going to be this.
Dr. Dregna, how do you know
Yep.
that? Because
yeah, I'm trying to think. So I know that because I'm looking at like a reference for it. I think I'm trying to think of like how the numbers come about. I guess generally speaking, the way to look at it, like if you're given an unlabeled graph, which I don't know that. Oops. I'm not sure like why that's considered important, but generally like the intersection. So like the ones that intersect, the one that's decreasing is going to be B, and the one that's increasing is going to be A. And then whatever the result is, like the resulting solution will be this line that kind of connects this point at the top and this point at the bottom. So the two lines that intersect, I think, are generally A and B. Yeah. So I think I don't know how standardized, I guess it's pretty standardized. I'm trying to think if I'm not super familiar with these graphs. I'm trying to think if there's a different way you could maybe draw this. Like for phase diagrams, for example, it doesn't matter like if this is labeled because I know that this is going to be the gas down here. No. I know that the gas is going to be over here. And then like solid will be maybe down here. I should know. Solid will be up here at high pressures. And then maybe liquid will be down here. No, God damn it. Liquid goes at the top. Solid goes down here. Anyway, you can deduce this. Apparently not quick enough, in my case, to do it extemporaneously while you're talking. But you can deduce it just from looking at the graph. I'm less sure about these over here, but this is fine though. And then so then all we're doing is once you know that, then it's just a matter of measuring it. So you'd go and look at the 60 notch and then come across onto whatever this is, and then drop that down here to look at whatever the mole fraction is. So on their diagram, I'm sorry, it's 80. On their diagram, they actually has like, increments so you can calculate it accurately. The mole fraction, so it's asking for the mole fraction of B.
The answer is like 0.2.
Yeah.
Because B goes from right to left.
B. Right. Yeah, so X of B is going to be going in this direction. Yeah, I don't know. So yeah, so if the mole fraction of A is 80, then you know that the mole fraction of B must be 20. That's basic. That's pretty much it. It's just understanding how to read the graph is really it.
number 15 is like slightly related to this question, and so I was a little confused by it. It's I know in GChem it was talking about how if you have volatile gases, you need to, I guess, somehow get this equation derived from Dalton's or Raoult's law, but it doesn't go into that too much of like a P1x1 plus P2x2 is equal to P. When I was originally trying to solve it, I was thinking it was like, oh, I have more moles of like ethanol or something, or I had more moles of methanol, so I was like, oh, I'm going to treat that like it was my solvent, and that ethanol is my solvent.
Oh, I see what you're saying, and use the methanol like a non. Yeah, that's like a pretty reasonable way to approach it. But yeah, I didn't go over Raoult's law in any of my lectures, but yeah, it's just a different equation.
Okay.
I'm trying to think of how you would know. I guess you would know the way to know to use Raoult's law if it does come to that. I mean, it's just a straightforward equation. It's not like it's what if you know to use it, it's not a big deal. I think the way to know that you have to use Raoult's law though is since they're giving you two vapor pressures, that's essentially telling you that they're both volatile. Like if they only gave you one vapor pressure, if you didn't know what the other compound was, you could assume it was non-volatile.
Okay.
Yeah, that's how I would do it. Or know to use that, I guess, equation.
Okay.
But yeah, both those questions, 14 and 15, weren't ones that we hit super hard. So those are reasonable points of confusion. I'd be really surprised if one of the graphs showed up on the exam. Raoult's law, I don't know. I could take or leave it, but putting one of those graphs on there, unless if it is on the exam, I guess I'll say it'll be more clearly labeled in terms of how to read it. Number 13. Yeah, so here's a problem like that's more straightforward in terms of calculating the vapor pressure change. Well, it's kind of in line, I guess, with what we talked about, where you have a non-volatile solute. And you're just seeing how that changes the vapor pressure. And so, what do we know? So let me get back to my. Yeah, so they're saying you've got our temperature is 20 degrees Celsius, and then we have a solution that's 0.61 grams. Why do they give you naphthalene? 0.61 grams of naphthalene. I see why this problem is confusing. 16 grams. Sorry. Chloroform. And then it tells you, let's see, can you do this without knowing? I think you have to know the molecular mass of naphthalene. So you know it's going to lower the vapor pressure, which is equivalent to raising the boiling point. Let's see. I think all we really need to do is figure out the mole fraction of solute. Mole fraction of. Yeah, you just need to figure out the mole fraction of chloroform. But to do that, you have to actually know the moles of each of those components. And I think that's, that's maybe the unclear part. So. I'm not insane, right? They don't give you the molecular mass. And sorry, I didn't write these homework problems. So, but they don't give you the molecular mass in the problem. So you have to look that up. Oh, they do. Oh, I'm sorry. They give you the formula though. Okay, cool. I was like, man, that seems really unfair. Okay. All right. So now we're good. Yeah. So all we're looking at is this, and we need to know the mole fraction of solvent that we have there, and that's multiplied times. So again, we're using that little 0 as the initial vapor pressure of the solvent. And so this is given as 156 torr. And so we just need to figure out what the mole fraction is there. And so we would calculate the molecular mass of naphthalene. So I'm going to do that quickly. And then the one for the bottom, which is 12. I can't remember what chlorine's atomic mass is. 35 maybe? 35.45. Another reasonable way to calculate the molecular mass for these is to look it up on Google. So these are close. I round off the 1.008 to 1 in my head for hydrogen. But yeah, now that I know that, I just convert over to moles. So I have 0.61 grams of naphthalene. Which means that I have this many moles of naphthalene, and then I have that many moles of chloroform. And so I just want the mole fraction. So the mole fraction is literally like, the sum over, or I'm sorry, the parts over the sum, similar to how you calculate like a percentage or something. So if I want to calculate the mole fraction of chloroform, I just take chloroform and put it in the top. And then I put the total amount of everything else in the bottom. I guess it's probably a good idea to be kind of precise when you're and not round that much when you're dealing with these, because the changes are pretty small.
So because they gave you the vapor pressure of chloroform, that's how you know to do the mole fraction of chloroform, not the other one.
Yeah, they also go on to say naphthalene is a low vapor pressure and maybe assumed to be non-volatile. But generally, yeah, I guess what I would say is if they give you a vapor pressure, then you assume it's volatile. It's not like 100% true because everything has a vapor pressure, like aluminum, like aluminum foil has a vapor pressure about it. It's just really low. But generally for problems that are set up for general chemistry, they'll just give you the vapor pressure of the one that's they'll give you the vapor pressure of the one that is volatile, because we don't give you a cutout. We don't give you a like a cutoff for where something goes from volatile to non-volatile. So you would have no way of guess. So I think generally we'll give you vapor pressure, the one that's the one that you need to plug in as the solvent. Where did the 0.138 mole come from? This is the 0.00. Did I like mess up my calculation here? Yeah, my bad. That's just the sum of the other moles that you have in there. The sum of everything that you have in there. So that should really be 0.1348. Yeah, sorry, I'm sloppy with my, I'm like really careful with my units and stuff, but I get kind of sloppy with the numerical rounding because maybe because I never did any kind of like real hardcore physical work. Physics, I feel like you have to be really precise. But yeah, then we end up with, let me recalculate it. Yeah, so on these, I was saying on these problems, it probably makes sense to be a little bit more precise just because the changes are small. And so that they can come out in the answer. So like here, when I was dealing with like calculating the molecular mass for this, I did some rounding in my head, you know, like maybe I called carbon 12 grams per mole instead of 12.01 and hydrogen just 1 instead of 1.008. And that might come back to kind of fudge your answer a little bit, which I don't know, on a multiple choice test, I don't know how much it'll, if you're close, it might knock you far enough away that you can't tell where you're supposed to go. But once you hit this, let me get rid of this side here. Then we can go in and calculate delta P. Yeah, actually, we'll call this P solution. So you're not calculating delta P, you're actually calculating P. We could calculate delta P, but this is more straightforward. But really all it's saying is that, like one way to read this is just that the 0.96, it's like whatever the original vapor pressure was, the fraction of the solution that is still volatile is just multiply times the original vapor pressure to give you the new vapor pressure. So as the solution gets more concentrated, the vapor pressure continues to go down because you have less and less of that volatile solvent still there. So here we're like 96% of, because 0.96, it's 96% still chloroform. And so we see that our change in vapor pressure is pretty small, 156 torr to 150.4 torr. But as this number gets smaller, So the amount of chloroform that's there gets smaller. That means the non-volatile solute gets larger. You can see that this number is going to decrease. So if this was 0.5, this would be closer to 75 over here. So that's sort of the result we expect. It's a super straightforward equation. But yeah, you got to calculate the mole fraction. That's really the only tricky thing.
I have a question for the LEs. If as long as we turn them in before Sunday each week, they should be contributing to a grade, right?
Yeah, and we'll probably drop some at the end of the semester. If you miss some, I wouldn't freak out about it.
Okay.
I had a question about the freezing point depression formula. In the lectures, it said it was I, K freezing, M, and then in DChem, it just said K freezing, M. So like, do we account for the Van Hoff or like no?
Seems to vary depending on what like book or text you look at. But you do need to always, the Van Hoff factor should get included in there. So there should be an I out front.
Okay, because
So
when
yes.
I solved problems, I just like ignored the I completely. Like, and if I tried to put I in there, it would like mess up the problem. So I didn't really understand like.
Really, for the freezing point depression?
Yeah.
So for problems where you're dealing with covalent compounds, I just equals 1. So those problems should work out to be the same. Like, do you have a specific problem where things got screwy? The only time I even really matters is if you have an ionic compound in there. So I could see how it would just end up working out to be correct regardless if you just happen to work problems where they're not ionic. But if you have an ionic compound in there, you do need to worry about I.
I was like, I think I found question 17. I might have just been like messing it up, but like I was just not sure about the I thing. It was on the homework too, question 17.
Yeah. So anyway, so I guess the answer is, regardless of the problem, is include I. Include I in there, and you'll always be correct. But you just need to know when I equals 1. Which question did you say? 15? No. Oh, free at 16?
17.
17. Yeah, so you should include I for this one. The ionic equation for this one is a little bit, I guess not so bad, but maybe it's maybe a little bit trickier than some of the other ones. So this is sodium dichromate. And when you put it in the water, it breaks up to sodium plus and just the dichromate anion. So you get one of these. So I should equal 3 for this. Does that clarify things? So you've got a solution of 8 moles. Let's see. So you've got a solution of 8 moles. Yeah, that should fix it. So you want to use 8 in your molal calculation. So it should be 8 over 16 multiplied times 3 times whatever Kf is.
Oh, I see what happened. Okay, I get it now. They did the 8 times 3, and so they did 24. Like I had to like look it up, like see how to solve it. And they did 8 times 3, 20, and they did 24 over 16, and so that's what happened. But I guess on Canvas it said 3 times the 8 over 16. So I guess I just got confused as to why they would do 24 over 16.
I see. Like they skipped a step in the answer key. Yeah. That comes from the I thing. So I think let me see on the answer I'm looking at, it's like they do it in separate steps. They call this like M effective, and then they say that M effective is equal to I times M. But there's no real reason to do it in 2 separate steps. You can just say delta T sub F is equal to I times whatever this constant is times the original molality.
Why doesn't a dichromate break up?
Like the short answer to it is it's just one of the polyatomic anions, and you just kind of have to memorize those and know that they don't break up. So it's the same reason. It's the same reason that like if you have sodium sulfate, that goes to 2 sodium plus in sulfate. There's a list of polyatomic anions. And cations, mostly anions. Don't break up. In solution. So just go find one of those lists, and that'll tell you why. But yeah, the longer answer is just that the ionic bond is between this, like in this top one, the ionic bond is between the sodium and the chromate. So, you know, there's a charge attraction between these two. If you look within the dichromate, these bonds inside of the chromate anion are themselves covalent. So that doesn't break up any further. Covalent compounds don't break up.
Oh. Okay.
Polyatomic anions themselves are covalent, and they're covalent compounds, and they form ionic compounds with cations, which, you know, sounds like a bunch of confusing stuff, but that's the reason.
Okay.
We're here, like, got a few minutes left if you guys have any other questions. So with these types of problems, like in the homework for colligative properties, you know, I don't know, like you can kind of get a feel for it that like being wrong about something or like making a mistake in these is easily corrected because the relationships are straightforward. I mean, this kind of stuff can be a little bit tricky, like to get caught up on. But if you understand the chemistry portion of it, like how the ionic things break up and where I comes from, like these types of equations are generally straightforward to kind of make corrections on. You know, like if you're off a little bit, like if you're thinking about things a little bit wrong, it's pretty easy to correct that. The molecular mass one was kind of hard, and this graph was kind of weird, but there's simple fixes because the relationships are nice and linear, and there's only like 1 or 2 steps. With the equilibrium stuff that we're moving into, I keep reiterating this just because I'm nervous about people taking it seriously, but the equilibrium stuff we're moving into is like, it's much harder to fix those problems. So I guess just be prepared to spend a lot more time on that, those extra worksheets and stuff. So, and I'll do office hours again on Wednesday. So just hopefully, I guess what I'm saying is, like get this stuff down if you've been working on it. That's great, so you can move on. But try to move on sooner rather than later, so that you're not caught off guard by the equilibrium stuff. We do have a good amount of time between today and the exam next Wednesday, but it goes quick, you know, like if you have an off day or something, you need to take a day off from studying, you want to have that built in.
What are we doing Wednesday?
I haven't come up with Wednesday's lecture yet. I probably, let's see, so we've got Wednesday, Friday, and Monday. I'm trying to think of what's left, really. Let me look at the homework real quick. Wednesday, we'll probably do another, it's going to be equilibrium stuff from here on out. Either Wednesday or Friday, I need to get to looking at delta G, looking at these equations. Oops, that should be looking at that kind of stuff, which are just short extensions from the equilibrium stuff. So I would guess on Wednesday, I'd probably work another, I don't want to beat it to death, but I probably work another equilibrium problem. And then I might start to try and tie it into free energy, and then Friday we'll probably just focus on free energy, and then Monday we'll probably just do some kind of review or something, depending on where we're at. I guess we have class on Wednesday too, so we could do a review on Wednesday. Yeah. So probably I'll do another equilibrium on problem on Wednesday, because those are the harder ones. But yeah, this is sort of what the rest of things look like. It's all K and delta G. So maybe another Rice table, but just looking at it from a different angle. And then I might try and tie it into this.
I have a quick question for number 17. Why would you subtract the 2.8 from like the normal freezing point, 273?
Wait, let me look up problem 17. Hold on.
It's because our freezing point always lowers in mixtures, right?
What would be the freezing point of solution to use the following values? Like how? Yeah. What's your question? Is how do you know to subtract and not add it?
Yeah. Like, would you ever have it, or is it like always going to be subtracting?
Yeah, I think the voice of God or whoever that was correct there. Because you're adding anytime you add a non-volatile solute, you know that the temperature is going to go. What's the vapor pressure? Freezing point. Sorry, you know the freezing point is going to go down. So it's always subtractive. Which is, I mean, it's intuitive if you think about it, because, well, less so for freezing point. But yeah, that's just the way things always go. It's the opposite of what happens with boiling point.
Thank you for your time.
Yeah, thank you guys. I'll see you guys on Wednesday, and we'll work some more problems, and I'll start trying to get the exam better together so I can kind of give you guys a good idea of what's on there.
Dr. Dragna, I have a quick question. It's actually personal. I emailed Ryan, the TA, but I didn't see your email on the syllabus. My grandmother entered hospice this weekend and is given days/weeks. Don't know that it'll actually interfere with anything, but at some point there will be funeral memorial service that I'll have to go to out of state. So I was just trying to be proactive as far as how to deal with that if it comes and it does interfere.
Just keep us in the loop. I mean, so you get one drop exam, so you can always use that. Most everything's online, so I guess just let us know if there's some way we can help out.
Yeah, it might not interfere at all, exactly, because everything is online, but just wanted to kind of be proactive. And
no, it's good to give us a heads up. Yeah, so just let us know, and to the extent that we can accommodate, we will. So just don't be shy about letting us know if you need stuff.
Okay, is there an email that I'm just missing in the syllabus that's your email?
Yeah, when you said that, I was going to go check on the syllabus. There should be one at the top.
Maybe I just missed it. It could be that simple.
Click on syllabus, there should be one right underneath my name, at least in the syllabus version I'm looking at, on the PDF.
Oh, on the PDF? Okay. That's probably, I wasn't clicking on the PDF. I was just looking at the.
Oh, like what the preview is of the PDF or something, or like the,
yeah. Okay.
Or maybe I see what you're saying, like on the syllabus on the home page that I pasted.
Correct. That's what I was looking at. Where is the PDF?
Yeah, I don't actually, now that I'm saying it, I don't think you can see that. Like I'm looking at, I think I have that restricted. Hold on, I'll just add my contact information to the homepage because it should be there.
Yeah, I was going to email you directly, but I just didn't see anything.
No, it's.
And like I said, might not interfere at all. Just wanted to be proactive.
Yeah, of course. Yeah, it's always a good idea to CC the TA on there as well, just because my inbox gets pretty clogged sometimes and I miss stuff.
Yeah, so Ryan got an email, whether, you obviously didn't because I didn't have your email, but Ryan did get one.
Okay. Yeah, no problems. Yeah,
I
thanks for being proactive.
Yeah.
All right, John.
Have a great day.
See you. Man.